Hi everyone, my name is Wei Deng. I'm a PhD student from University of Southern California. Today I'm going to present the nonlinear analysis of full-day leg movement between infants with typical development and infants at risk of developmental disabilities. Wearable technology has been more and more popular nowadays, with sensors in all kinds of wearables. This also enables researchers to measure human behavior in a more natural environment for a long period of time. Traditionally, we have been using accelerometers such as Fitbit and Actigraph to measure movement frequency and intensity. The newer sensors also included gyrometer or even EMG. This enables us to measure the certain types of movement or muscle synergies and more. However, none of these analyses capture the dynamic nature of infant behavioral patterns. One way to measure that is using the nonlinear analysis. Nonlinear analysis is different from linear analysis. Traditional linear methods, such as standard deviation, tell us the amount or magnitude of changes. However, it assumes each movement is random and independent of previous and future cycles, which is not true for biological movements. Each biological movement is influenced by the previous movement, and also it will influence the next one. On the contrary, nonlinear methods tells us the temporal structure of movement patterns. So how does it change over time? The figure on the right side gives a good presentation. It may look like random noise, just like human movement, but there's actually a hidden structure behind it. Our aim for this study is to explore leg movement's nonlinear variability across a full day in home environment in infants at risk of developmental disabilities and infants with typical development. We hypothesize that the sample entropy of acceleration and angular velocity is different between the two groups. We interpreted higher sample entropy as higher nonlinear variability. We recruited 11 infants with typical development and 9 infants at risk. We put a sensor on each ankle for 2 days with at least over 8 hours of wake time each day. As shown in the picture, the sensor is really small, and our previous study shows it did not affect the amount of movement infants made. After we got the full day data, we divided it into 5-minute segments and calculated the active segments, which means there were at least 50 movements in the 5-minute section, with an average all the segments for each variable. The result shows that the two groups have significant differences in the nonlinear variability of acceleration and angular velocity data. If you look at the left figure, x-axis shows the two groups and y-axis shows the sample entropy value for acceleration data. Blue is left leg, orange is right leg. This is the same across all figures. So we see that both legs in the typical developing group have higher nonlinear variability of acceleration than the at-risk group. On the right side, the results from the angular velocity show similar pattern. The y-axis shows the sample entropy value for the angular velocity data. We see that both legs in the typical developing group have higher nonlinear variability of angular velocity data than at-risk group. Interestingly, the linear analysis shows the opposite. So we use the standard deviation for peak acceleration to measure the linear variability. As you can see in the figure, the y-axis shows the standard deviation for peak acceleration. At-risk group on the right side have significantly higher linear variability of acceleration on both legs comparing to the typical developing group. To summarize, at-risk group have lower nonlinear variability, and we interpreted this as more repeatability for leg acceleration and angular velocity than the typical developing group. And at-risk group also has higher linear variability for leg acceleration than the typical developing group. We interpreted this result as the at-risk group have higher magnitude change, but their movement pattern have lower complexity, and the typical developing group has relatively smaller magnitude change, but their movement pattern have higher complexity. There are some limitations for this study. First, we have a relatively small sample size, and the at-risk group are very diverse. Some are preterm, some have congenital disease. but this represents the typical population we see in clinic. Lastly, the full day data include both awake time and sleep time, and different positions. Future studies should look into these different factors. We hope to relate this result to motor development trajectories or neurodevelopmental outcomes in the future and help with early diagnosis of developmental disabilities. Thank you.